So for the last talk of this session, we will go with Justin Carpentier. So Justin is one of the two former students of Jean-Paul that was selected for one of the talk of today, which is saying something about his excellence, of course. Maybe something more accurate with that. So you know that Jean-Paul was very active in keeping his students close to him, with the example of Philippe, of course. But in the case of Justin, it was not possible anymore. Time has changed, so Justin has to move to Paris. And maybe it's a coincidence, but Jean-Paul decided to move right at the same time and stay very close to Justin, to his last student. So Justin is maybe the best consequence, or the best, I don't know, best consequence of the fine alloy that Jean-Paul forged with Aichi in humanoid robotics, with his own career in geometry for robotics and in numerical optimization with Katia. And Justin took all of that for himself in his research. He's the guru of the library Pinocchio that maybe most of your group is now switching to if you are working with serial chain robots, human robots. So maybe you can take some time to say thank you for all the night he's spending on that. Today he will try to give a picture of the last research that Jean-Paul was driving with him in Paris. So with his thesis first in Toulouse and with his early career in Paris. So Jean-Paul, Justin, the floor is yours.
Okay, thank you, Nicolas, for the nice introduction. So hello everyone, I'm Justin Carpentier. So I'm a researcher within the Willow team at INRIA Paris. So working with Jean, with Jean-Paul at this time, and also with Ivan Laptev and Cordelia Schmidt. So we are working on trying to make the intersection between vision, perception in general, and robotics. And also we are trying to work together with people in machine learning and optimization to bridge the gaps for building what we call the computational foundation of artificial motion. So in fact, I met Jean-Paul like 10 years ago. It was in this room, so just the room upstairs, I think. It was at Collège de France. So this is the inaugural lecture of Jean-Paul here, so in January 2012, sorry. So I was just on the left. And for me, this was the first time that I've seen robotics written as mathematics. So just to let you understand what was my mind at this time, it was that robot is mostly a toy that we can play with. So this is the French Robotics Cup, which is a yearly program in France to work with robots. And this is a fantastic way of diving into robotics. But for me, at this time, robotics was this kind of things. So playing with robots, trying to build robots, and trying to program robots. And then, so during the class of Jean-Paul at Collège de France, so this is the class of Jean-Paul, so which was in this same room, in fact. So we have two people, no, at least, so three people in this room, which was involved in this demonstration. So this was the first time that RTP2 went out of class, or maybe not one of the first time, but at least for teaching robotics in Paris. So this was a bit exceptional. And so this is, I will just let you see, sorry, there is no sound. There is a okay, I will try to give you the sound.
La trajectoire a été préprogrammée, mais on vous projette en même temps, donc vous pouvez vous reconnaître ici, hein, par exemple, prêt à prendre la photo, donc vous pouvez prendre la photo ici. Hein, tout le monde est là, donc vous allez voir, donc projeter ici ce que voit le robot. Voilà.
So this is a demo of Usama Kanoun demonstrated by Aichi. So on the real robot. So this was pretty amazing for young people.
Sa main apparaître et on ne distingue pas très bien l'objet s'il est là. Oui. Alors vous voyez ici la forme anthropomorphe dans toute sa puissance. Hein. Donc là, tous les degrés de liberté ont été utilisés pour prendre cet objet au sol. Encore une fois, comprenez bien, cette trajectoire est issue des calculs automatiques que Nicolas Mansart vous a présentés. On n'a jamais dit au robot qu'il fallait reculer.
So this was very impressive, at least for me. A bit a mystery, but so that's why I decided to move and to join this team. So this is a Gepetto team in 2017, if I remember well. So we can recognize a lot of people in this room. So the idea is that, at least for robotics, what we should understand that we need robots, but also we need people to make this robot work. And this was a fantastic journey to join this team and to understand how we can move robots. So now for me it's time just to move on because I think the time is running. But I just want you to introduce the main result of my PhD, which has been under the supervision of Nicolas and Jean-Paul, of course, and with a joint work with Mehdi Beneleg, mostly. So at this time, so it was in 2014, most of the robots were using very simplified model to move. The most famous one is a so-called card table model, which is this representation where we have a mass which is just evolving at a constant height. And this implies very major limitations in the motion of robots. So the whole picture and the whole understanding of Jean-Paul also in this frame was also maybe to try also to go beyond these simple models, but also to try to understand what are the models beyond humans. And of course, human is not evolving with a constant altitude center of mass, and so we need to think further. And so the main question that we asked during my PhD, and also maybe still today, what is a good model to analyze and control anthropomorphic locomotions? So if I come back just to the basic principles, so this is the human body, and if I'm just a human body, I'm subject to gravity, and with gravity, I'm falling. So the gravity, in fact, to avoid to fall, we need to create contact interaction, and if we look to this contact interaction, they are acting on the virtual point, which is nothing more than your center of gravity plus the angular momentum. So these things, if you're able to control these quantities here, it means that you are able to create and to build movements and to move forward and to locomote. And this is the real idea of my PhD, but this is the same idea that many teams in the world have followed. So like the team of Ludovic, for instance, also Pierre-Brice, if I remember well, there was also the team up there in the room. So it was a general idea in there. So what we have done first is that we have first tried to analyze human motions. So for that, we have equipped people and so on. We have recorded motion, a lot of motion. We can see here Jean-Paul, which is just attending the recording session in Toulouse. And so from these measurements, what we have tried to do is to first build what we call estimator of the center of mass, because this is a virtual point which has no existence, but we need to try to recover this information from data. So data means motion capture markers plus force plates measurements. And from that, what we have observed is that the center of mass, if we just draw it from this estimator, we can see that there is a given geometry. And in fact, if we analyze this geometry, you can see that it follows what we call a cycloid. Yeah, thank you, Philippe. So it follows a cycloid, which is just the motion of a point on the radius of a wheel. And so we have done this analysis, and we have tried to highlight the fact that for many people, so I think there were 25 people registered, we can find a linear relation between the size of people and these two numbers. And as we will see at the end of this presentation, so I have a bonus for everybody, that the wheel was like a vector of direction for Jean-Paul along his career. So starting from the beginning, I think, Atlas NRS, until the end, it was the wheel which was motivating largely his research. So from a humanoid perspective, we try to move forward and try, so as I remember, to remove this assumption of a car table model, so having a center of mass which is evolving on the plane. And for that, we use this famous central model, which is a bit more complex to use because it's a non-convex quantity that we need to control, and for that we use optimal control. So we use a tool that Heidelberg University was providing, to call Muscot, to drive the locomotion of robots. And for that, as a team effort, we built this world computational pipeline, which was a bit unique at this time. So meaning that at the first glance, what we try to find is the contact planification of the end effector motion of the robot, like the feet and the hands. And then the second stage of our planning was to compute the so-called centroidal dynamics together with the contact forces. And then from that, we can just use classic whole body controller in order to track all these quantities and to move forward. And all these things have led to a generic framework and a generic approach with a single program able to generate a large quantity of motion, while at some point it was not possible to go so far at this time. So here we have just a generic locomotion on the HRP2 robot. Maybe it was one of the latest experiments that we did on this robot. So on the right, we have just the same robot with the same program. We just change the footsteps, and we are able to climb stairs, which is pretty easy. So I will move a bit forward. And so here we have the same thing, but now we are trying to use the on-rail. And so this was the setup of the CoreBot project led by Katja and also co-led by Philippe. And just to show the difference, so this was a bit at the same time at the DARPA Robotics Challenge. So this was the Atlas robot of HMC team, and this robot was not using at all his hand in order to climb the stairs. All the idea from in the air at this time was ready to try to exploit the environment to move forward and just move much more faster, because here you can see that the motion is 4 times accelerated. So I will move now forward just to illustrate a bit the perspective of research that we are trying to bring in Willow, and this was done with Jean-Paul. So just robotics, where do we stand today? So of course, so as mentioned by Jean-Paul at initial session, so robotics was a very young field of research, but with a great impact, so like automation in manufacturing, mobile robotics. But as soon as we want robots outside of laboratories, of industries or plants, this is a failure. This is a strict failure because we are not very able to handle all the complexity of the environment, and mostly we are not able to properly interact with in controlled settings. So how we can move forward and how we can achieve this thing? I think we need to step a bit back and just try to understand how we control a robot. I think most of you are already familiar, but for those who are not familiar, so there is the physical space. This is the space where all the forces, Newton forces, occurs. So this is the ambient space. And from this ambient space, we only have a perception of this environment through our sensors, so like cameras, accelerometers, and encoders for robots. And then from that, we need to take a decision at each instant in order to control our motor space with muscles or just electrical motors, which produce action in the end in the environment. And this is what we call often a control policy or control law in control theory. And so the whole idea of robotics, or at least at this level, is to build a mapping between sensor information and control outputs. So there is at least now 2 ways of controlling robots which are very well advanced. So the one presented, in fact, by Philippe this morning, which is just optimal control, which is a generic setting for the controlling system, from which we can also extend the notion of optimal estimation, so meaning that we aim at inferring the state of our system according to the input measurements, and from that we aim at optimally computing the control output to control the system. So this is the Russian way of thinking about control. And on the other side, we have something which is now exploding in our community, which is policy learning. So what it means, instead of just thinking about a single trajectory, we try to find a world control policy, pi of theta, in order to control our systems. So in a raw picture, what we are trying to do is just to try to build with often neural networks to build a relation between inputs and outputs by learning. And for that, we need to generate often billions of simulations in order to really capture and control the system. And this is coming from all the theory of Richard Bellman, which were provided almost at the same time. And so from a picture point of view, what we are trying to do at the optimal control level is that we are trying to identify control trajectory and state trajectory over the time, while at this level, what we are trying to do is rather to try to capture the whole vector field. So this is illustrated by this illustration. So on one side, we have trajectories. On the other side, we just want for each time instance and for each state, quantities, we want to infer what is the right control to apply. And this has provided very nice results. So for instance, in optimal control level, we have Boston Dynamics, which is now, I think, state of the art, we can say, for generating highly agile locomotions. So this is based on the same principle that I have presented before. So just computing online trajectories. So this is planning, online planning. On the other side, we have policy learning, and with nice results from ETH Zurich and from the team of Marco Hutter, where the robot is able to encounter very versatile substrate and just to be stable. So now it is not yet clear how we should move forward within the community. I think I will try to draw some important problems that we are trying to solve now in our team, at least, but not necessarily in our team for this one. So the need of a good design. And I think this is illustrated here by these small robots that we can see. So I just let's run, and you will, I think, totally understand the principles behind this video. Okay, so then we have different aspects. So from physics, we only partially understand and capture complex physical phenomena. And I think, so as we have seen that both optimal control and reinforcement learning or policy learning needs a simulator to capture the physics. And so I think we need to move forward on how to simulate complex phenomena, because we are, for instance, just only using very simplified model of the contact phenomena. In terms of control and learning, I think there is a strong interplay between policy learning and trajectory optimization, but we are not able yet to exploit it. And this is something I think very prominent to focus on if we want to accelerate the learning of control policy. From an optimization perspective, we have dedicated middle and solver for robotics. We need that, and currently we are mostly using off-the-shelf solvers, which are not sufficient if we want to target autonomy of robots. And then from a perception perspective, we need to fusion sensory information to move forward, and we are not able yet to do. So to move forward, so we have several students in the team here, which are all listed, which are working so both to make progress scientifically, but also to make progress as a software perspective. So as mentioned by Nicolas, so we are trying to build, in collaboration with Toulouse, still to build like a set of software which can be very versatile and very useful for all the problems that we can encounter in robotics for manipulation and locomotion mostly. So before finishing, I just want to finish by this sentence from Alexandre Grothendieck, which mentions like 30 years ago that he was convinced that time is the only decisive test for the fertility of new ideas and of views. Fertility is measured by offsprings, not by honors. So I think in this room there is a lot of offspring of Jean-Paul, either by ideas or just by careers. And I think this sentence summarizes a lot the career of Jean-Paul.